So for section 5, we looked at sine and cosine. Section 6, we're going to look at the rest of them. Start off with tangent. For tangent, what's it look like in general? Anybody remember?
TAN.
It kind of looks like x cubed, except it repeats, and you have a bunch of what? Asymptotes. So those asymptotes are going to occur at every pi over 2, and then every n pi thereafter. So anywhere where you still see it over 2 where it doesn't simplify out, you can also could describe it as every k pi over 2 where k is an odd number. You can describe it a few different ways and it's fine. Those are your asymptotes, so then your domain is everything but those. Now, why are those occurring at pi over 2? Think about what tangent is made up of. So that's when cosine is 0. Because the denominator of tangent is cosine, at every pi over 2, 3 pi over 2, so on and so forth, it's going to be 0, so the fraction becomes non-existent. Okay? The period of the function is also just pi instead of 2 pi. Now there's a couple different ways you're going to go about graphing these. The biggest thing is to get those asymptotes, figure out where they are at. Okay? You could use the period and then just adjust from there. You can also just use this technique. This actually works pretty slick for these because those asymptotes can be hard to actually place. So I will actually use this for these asymptotes, where it's the same idea as the endpoints for one cycle, but it's a little bit more clear what's going on with this. So you just take what's inside the tangent function and set it equal to the two closest asymptotes to 0. So negative pi over 2 and pi over 2. That'll give you one cycle, and then you can adjust from there. So if I have this, I have y equals tangent of x over 4. All I'm going to do for this is take what's inside of tangent. So x over 4, set it equal to, well, the asymptote negative pi over 2. What is that asymptote going to turn into? It'd be negative 4 pi over 2, which simplifies to negative 2 pi. You just solve for the x. The other asymptote was at positive pi over 2, so that would just be 2 pi. So when I go to graph this, I'm going to go left, negative 2 pi, right 2 pi, and I'm going to actually show a couple cycles of it just so I can see it. So I'd go out to 6 pi this way. Because this actual period then is what? From here to here? 4 pi. So it's going to go through the origin. You have asymptotes there and there. So your graph looks roughly like this. Now, this is nowhere near to scale. So 4 pi would be there, 6 pi would be out here. And again, it goes through the origin and up. Okay? What if instead I had tangent of 2x? What would the period of this function be? Well, careful, because default period for tangent is what? Yeah, default period for tangent is pi. You still do the default period divided by b. For sine and cosine, that's 2 pi. For tangent, it's just pi. So this is just going to be pi over 2. So if I go to graph it this way, and I'm just kind of showing you this way because it ends up being a little bit harder to visualize what's going on. The period's pi over 2, but what that's going to do as far as where this thing hits, it's still going to hit the origin because I don't have any kind of phase shift or vertical shift going on. But now the period's pi over 2. So I'm going to go left and right how far? Pi over 4. Because I need the width to be pi over 2, right? The whole overall. So I'm going to go left and right pi over 4 in order to get that to be pi over 2. Okay? And then again, that's going to go up and through the origin. It's going to hit the origin again at pi over 2. Then at 3 pi over 4, it's going to have another asymptote. And it's just going to repeat like that. So on and so forth. What about cotangent? What's going to be the difference between cotangent and tangent? Graphically. No, they're not inverses of each other, because inverse tangent would actually go like this. It'd be like a long S looking thing. The asymptotes are going to be different because tangent is sine over cosine. The asymptotes occur when cosine is 0. For cotangent, it's going to occur when what? Sine is 0. Okay. The other thing that's going to happen is you're actually going to end up starting high and ending low for these instead of the other way around. Okay. But notice the asymptotes are now at 0, pi, 2 pi. They're every n pi. Okay. So if I had one that looks like this, I want to sketch the graph of cotangent of x over 4. Now I can still take what's inside the cotangent and set it equal to the old asymptotes, but where are those old asymptotes at? That was on tangent. Pi and 2 pi, or I could actually even go smaller than that because it also is just equal to 0. You do 2 pi as well. So for this then, x is going to be what for that top one? 0. And for this one? 4 pi. So this one actually is on the y-axis. You have an asymptote. So that's one of your asymptotes. The next one's going to be out here at 4 pi. And then at 8 pi, so on and so forth. And then this also, it's going to hit halfway between each of them, but it's going to start high and end low. Okay? Yes?
I'm kind of confused where you got 0.
Because on cotangent, the old asymptotes are where sine is 0. Sine is 0 at 0, pi, 2 pi, so on and so forth, right?
Mm-hmm.
So that's what I set equal to what's inside the cotangent function. So I take what's inside of here and set it equal to those old asymptotes. Because that'll adjust those asymptotes based on whatever phase change or phase shift and whatever period change is going on. When you're doing tangent, those asymptotes are pi over 2 and negative pi over 2. When you're doing cotangent, it's 0 and pi.
It would be that every time?
Because that's the default for regular old, if you just have y equals cotangent x, it's going to be 0 and pi. Then this change is what you're applying to that. So it's kind of that parent function and then transform function thing. Okay? Any other questions? Okay. Now, when we do the other ones, secant and cosecant, will those have asymptotes?
No. Yes. No. Maybe.
Why?
Not sure. Because
They're the reciprocals of what?
sine.
Sine and cosine. They're going to have asymptotes the same way that tangent does, because if you look at secant and tangent, those are both over cosine. So those are both going to have asymptotes at negative pi over 2 and pi over 2. Cotangent and cosecant will have asymptotes at sine. Okay? So, I cheat though for these. These are actually end up being a little bit easier.
Ooh.
Okay? What I end up doing instead is what this book does, where it'll graph sine and then use the fact that everywhere sine is 0, you have an asymptote to draw those asymptotes. And then wherever you have peaks and valleys, cosecant will come down and hit the peaks, come up and hit the valleys between those asymptotes. Okay, so what I'll do is I'll graph these key points here. And then I'll just draw in the asymptotes and draw in those curves that come down and hit. Okay, so if you can do sine and cosine stuff from yesterday or from Tuesday, this is the same stuff, just you do something different with those points. So, if I have y equals 2 cosecant of x plus pi over 2, I'm actually just going to find those key points for sine. Because this is 1 over sine, I'm just going to do 2 times sine of x plus pi over 2. And then I'm going to use those points to rough sketch cosecant. So I'm going to go through the same process we did up here, where a is equal to what? 2. B? 1. C, negative pi over 2. And D, nothing. So, amplitude is what?
2.
The period would be
2 pi.
2 pi. Phase shift,
Negative pi over 2.
negative pi over 2. Since the 2 pi is just divided by 1, the negative pi over 2 is just divided by 1. Those are just going to be how they read. So, what I'm going to do then is graph those points. The period is pi over 2. This is sine, so it would normally hit at the origin. The period is still 2 pi, so then it would hit again at pi and 2 pi, right? This phase shift, though, is going to cause those x-intercepts to do what? This phase shift is going to cause these x-intercepts to go where?
To the left.
To the left, because it's negative and pi over 2. So you have these that were here are now here. I don't have any kind of vertical shift, so that's going to be where they stay. Let's see, so about there. Now normally, this was at the origin a second ago. From this x-intercept, you go up or down?
Up.
Up. So you go up until you hit a peak of what? 2, halfway between those x-intercepts. So if I go up 2, that's going to hit there, come back down. It's going to have a low point at negative 2 between these, and then it's just going to repeat that pattern. Okay? Now I'm not going to draw any of the curve there because I don't care about the sine curve. I'm going to use these reference points though, because where are my asymptotes going to be? Where the sine would hit the x-axis. So you have asymptotes wherever you did have x-intercepts. Okay? Then, wherever you have peaks and valleys, since this one's the peak, cosecant is going to come down, hit it, and go right back up. And it's just going to repeat that pattern. That makes these ones fairly easy to draw. As long as you can do sine and cosine. Okay, let's look at another one of those. If I had secant of pi x, what would I need to do? Where would I start?
Rewrite it as cosine.
Yep, write as cosine pi x. Then?
Find the amplitude.
Yeah, find all those. I would actually do it with that whole ABC thing. If you don't have to do that, that's fine. Especially on one that's boring. What's the only thing that's different from the norm? The pi. What's the pi? It's not the period. It's the b value, yep. So a is still 1, c is 0, d is 0. That pi value, or the b value of pi is going to mean what for the period?
It's 2.
It's just going to be 2, because you'd have 2 pi divided by that b value, so it's just going to be 2. So when I go to graph this cosine, the amplitude is still 1, so it's still going to go up and down 1. There's no phase shift, no vertical shift. So this thing's going to start up here at just 1. Okay? When will it be up at 1 again?
2.
At 2. So I'm just going to put 2 out here somewhere and mark that point. Where's it going to be at for 1?
Down negative.
Down at -1. And then just repeat. Okay? Now, I'm not even going to bother with the x-intercepts because I know the x-intercepts are where relative to all these points?
Halfway.
Halfway between. So my asymptotes are going to be halfway between. Try to make these vertical, but... Then to put in the curves, just make sure you're between the asymptotes. And do not cross the x-axis. Or the midline if it's moved more severely than this. Questions on any of it so far? Okay, one last thing I want to look at is what's called a dampened trig function. Okay? Now if you talk about dampening sound, what's dampening sound mean? Doing what?
Using it.
Reducing it. Okay? reducing the actual effect of the sound waves. Okay? In this case, dampening can actually mean increasing or reducing the amplitude of sound waves, or waves in this case. Okay? So what this does is it applies something to the front of the function that will change what happens with the function. Well, normally, the number in front of sine affects what? The amplitude. This being an x means you're not going to have a set value that sine's oscillating in between. You're going to have a value that changes as you go. Now, honestly, they make this fairly complex with looking at how that x affects it. Because sine bounces back and forth between a negative and a positive, this x value's effect is going to bounce back and forth as well. So you actually just don't have y equals x here. You have both y equals x and y equals negative x going on, because it oscillates between them. As sine goes on, it flips from -1 to +1, right? So where that would be 1, though, it's going to be whatever the x value is. So what they do is they rewrite it like this. Honestly, I'm not going to expect you to come up with this equation. But that's what it ends up doing. It oscillates between those two. Graphically, it ends up looking like this.
Oh, that's a nice.
Okay. But if I look, what this is doing is, instead of hitting at 1, at pi, this x value is up here. So halfway between, it would be pi over 2, it's going to hit there. This would be 3 pi over 2 down, in other words, 1.5 pi down. This would be at 5 pi over 2 up. And it's going to bounce back and forth between those. Okay? Now, your calculator will do these. And you can do them on the calculator, that's fine. But I want you to realize what's going on with them. Okay? Because if I have this one, e to the x times sine 4x. Well, what's e to the x look like?
Natural law.
No, just e to the x. What's just regular y equals e to the x look like? It's an exponential. It's just as if it was 2 to the x. It's just a line that curves up, right? It approaches the x-axis, or starts off really close to the x-axis, and goes up. So the idea for this is it's going to look roughly like this. It's going to go through 0, 1, and then just go off into space. But the thing is, because sine oscillates between a positive and negative, it's also going to be down here. And that's what you're bouncing back and forth between. So if I'm doing a rough sketch of this thing, all I need to know is that it's going to go through 0, 0. And it's basically just going to do, it's kind of hard to see at the beginning, it's going to bounce back and forth between. I should have been going up at first, but you will have your calculator for this. I would not ask you to do this without at least having that reference. But it's going to end up looking like that, roughly. If you do it on the calculator, I'm actually going to graph all 3 parts. There's only the last equation actually matters here, but I want you to be able to see that it's approaching those 2 lines. I'm going to just do zoom trig so I can have it standard. There's that y equals e to the x. There's y equals negative e to the x. And then the sine will oscillate between the 2. Okay, never going beyond what that e to the x limitation on the amplitude is. Does that make sense? All right. Now, you can also dampen the function the other direction. You can come in, start really large, and then come down so it just gets really, really small as you go. The only thing is, you can't do an exponential growth one then. You'd have to do what? Exponential decay. So you can actually end up getting one that looks like this as well. Just with e to the negative x and negative e to the negative x. Questions on any of it? Okay. Next week, we'll take a look at sections 7 and 8. Those we're going to spend a couple days on a piece. So,